Okay, thank you very much, Sky. Thank you for the invitation to speak here. So I'll be speaking of joint work with Barbara Dembin, who's at ETH Zurich, and Dor Elboim, who's here at Princeton University. So what is the first passage percolation? This will be the model that we'll talk about. So as an idea, first passage percolation is a random perturbation of Euclidean geometry. Okay, and with some additional specifics of how it is, of what does it mean to be a random perturbation. In particular, the perturbations will be local and independent. So this is an idea, but then let me give the specific model that I will study, and I will not talk about any other model for first passage percolation in this talk. So when you do it on the z-squared lattice, and this is the context of planar first passage percolation that will be in this talk, then what you have is a collection of weights assigned to the edges. So edge lengths, random edge lengths, let's call them. Edge lengths, tau e for every edge of the square lattice. So you see, for every edge, I have a number, and these tau e, they are IAP, meaning independent and identically distributed, and they're non-negative. And that's all you need in order to start. But in this talk, I will also assume, and some of this is for simplicity, that is, our proofs can go a bit beyond, but I don't think it will be a problem for us, that the distribution of each tau e, it's the same distribution for all of them, is compactly supported in zero infinity and absolutely continuous. Okay, so let me now explain what do you do with these weights. So the idea is the following. I have the z-squared lattice, and the z-squared lattice is a metric space. In what way is the z-squared lattice a metric space? In the z-squared lattice, if I want to go from a point to a point, I can count how many edges I will use to go from here to there. So it's a metric space by counting number of edges. Now I'm going to make it into a random metric space by using the numbers on the edges as my edge lengths. So for each UV in the z-squared lattice, I define the passage time PUV as the as the minimum over paths P from U to V of the sum on the edges along the path of this tau e. So this means the following. When I want to go from the vertex U over here and to the vertex V over there, I have to look for the shortest way, and this time I sum the numbers along the way. So here, depicted in blue, is the shortest way, at least according to the weights that I see in this picture. So it's a random metric. So P is a random metric on z-squared. And at the same time, let me also introduce the idea of a geodesic. The geodesic is the minimizing path, the minimizing P, and I'll denote it, denoted gamma UV. So the blue line above is the geodesic between this U and V. And what is the goal of this endeavor? The goal is to understand how the random metric looks like. So study the large scale properties of T. And in particular, these geodesics, properties of T and its geodesics. All right, so I thought that I'll begin my talk intended for non-specialists by saying what is expected. The physicists have an elaborate picture that is expected for this model. However, the mathematicians have not been able to justify most aspects of this elaborate picture. So let me call this basic predictions, and actually they can go much further. So when you see a random metric like that, and you have in mind two very far away points, maybe I have this point 0, 0, and this point L, comma 0. And I want to know how does the minimizing path between them look like. If this was just the z-squared metric, then the minimizing path would be the straight line segment. By the way, I forgot to say that by the absolute continuity assumption that they have, every path between U and V has a different sum of weights, so there is a unique one which minimizes. It's also easy to see that it exists. So there will be a unique path, a unique geodesic, and how will it look like? If it was just the z-squared lattice, it would be a straight line. So what would be in the random case? And okay, we may expect it not to be a straight line, although we may expect that it still kind of is close to the straight line. So maybe it looks roughly like that. Maybe it goes a little bit back, goes forward, maybe hits it from the other side. But in principle, something like that. So we'd like to make this picture a bit more quantitative. We have a length scale in this picture. This is a length scale L. So a question we may ask is, what is the transversal length scale? So how high do I have to look so that I capture most of the geodesic with high probability? And the physicists usually denote that by an exponent psi. For instance, if you have a Brownian motion going from here to there, then we know that the transversal fluctuations of it will be of order square root of L. So for a Brownian motion, psi is a half. Is the geodesic in the random metric super diffusive, more than a half, or sub-diffusive, less than a half, or maybe exactly diffusive? It's a question. And then you may also ask about the time itself. What is the statistics of the passage time to get there? So here are some of the basic predictions. So consider the passage time t from 0 to L times V. So this means I'm going from, I have a 0 here maybe, and there is another vertex V over there. And I'm going not to V itself, maybe V is here. I'm going not to V itself, but rather very, very far away in the direction of V, like so. So I want to know as L grows, what will I see? And then the prediction is the following, that the expected passage time, T0 LV, is governed by a direction-dependent first order. So the fact that there's an L factor should not surprise you. If I want to go from 0 to distance L, then I need to sum at least L weights. And each of these weights will have some non-zero mean. So it's very reasonable that the first order contribution will be something times L. However, on top of that, there may be additional fluctuations. And indeed, even in the expectation, there should be a correction of order L to the chi. This is again a physicist notation. There is a chi and there is a psi. And the standard deviation of the passage time should be some other c, L to the same chi, 1 plus little o 1. So, and there is also a limiting distribution associated to it. So it's supposed to be a Tracy-Widom limit distribution for the passage time. So this would constitute the very basic predictions, that there is a exponent that governs the fluctuations of the passage time. This exponent is chi. And there is another exponent that governs the fluctuations in space. This is the exponent psi. And the physicists also tell you what these exponents should be. So the big conjecture here is that chi is 1/3 and psi is 2/3. And all this and much more is the so-called KPZ universality class. So notice in particular that psi is 2/3, meaning that the geodesic is super diffusive. So it is interesting that the minimizing path is not like a random path in the sense of a simple random walk or Brownian motion, but somehow it pays for it to go a little bit further than what a simple random walk does, in order, I guess, to obtain a smaller weight environment. It looks where is the smaller weight environment and goes there. There is a picture by Hammersley and Welsh of highways. So they use this term. In this random metric, there are places which are highways. They're faster than others. So the geodesic seeks the highways. And they could be a little far from it. That's why it goes a bit far. Okay, and elaborate on this first order behavior as well. You see that it's a direction dependent first order behavior, mu of v. So here, mu is a deterministic norm. You can do it on r squared. Doesn't need to be on z squared by homogeneity. Is a deterministic norm on r squared depending on the distribution of tau e, on the edge weights distribution. What do you think? Which norm is it? So you may, those who have some experience with statistical physics and know about universality may expect it to now be rotationally invariant, because we know that Brownian motion is rotationally invariant and things usually become that way. However, it seems that it is not a ball. It seems not to be a ball. And in fact, there is not a single weight distribution for which it is known. Not known in any case. And so never known explicitly so far. However, we do know that it exists at least. I'll get to that in a second. We usually denote by B the unit ball of mu, so that T times B is places get to time less than or equal to T. So let me say a bit more about that. So we do expect that the limit shape B is somewhat close to roundish usually, although it's not supposed to be a ball, depending on the weight distribution. So this means that if you're going in this direction, maybe it's slightly easier to go than going in this direction, depending on the shape. It tells you in each direction how fast you go. And it kind of makes sense that it wouldn't be the same in all directions, because if you're going in a diagonal direction, you see that on the lattice you have, in a sense, more ways to go diagonally than to go horizontally. It kind of makes sense that it could depend on the direction, and it seems that it does even in the limit. So maybe I should have written also a formula. Mu of B is really the limit as L goes to infinity. So T rho LV divided by L. This limit should be almost sure. Okay, so and the further conjecture is that the boundary of B is strictly convex. Okay, maybe I'll leave it like that. So second derivative bounded from 0 and infinity in particular exists. Okay, so this
that's a crucial point, right?
That's right. This is a crucial point. So the fact that the boundary of B is strictly convex, as opposed to, for instance, a picture of this style, so the L infinity ball, tells you the following. If it was the L infinity ball, you can imagine how geodesics in the L infinity norm look like. Suppose I want to reach from here to here, then in an L infinity metric, there is not much loss in doing something like that. So this could be a geodesic in L infinity metric, and by this picture I mean that this length scale, this is 0 and this is LE1, and this height is itself, I don't know, 1/10L. So this deviation, which was on this board supposed to be L to the 2/3, if you were to do it in an L infinity metric, would go all the way to L to the 1. The reason that it should not is that certain directions are so much less preferred that if you go in those directions and try to come back, you'd pay more even in the linear scale. So the strict convexity is related to the fact that this is strictly less than 1. Okay, so what is known then of this elaborate picture? So we know very little. So we know that mu is well defined. This is the subadditive ergodic theorem. Additive ergodic theorem. And it's a norm, so we know its unit ball is convex, but we don't know that it's strictly convex. Okay, we know a little bit more, not much more. Don't know, so we don't know even that B is not the L1 or L infinity balls. So we're lacking a proof, even under the assumptions that are written here, that the limiting metric is not the metric of the z-squared lattice, the L1 ball, or the L infinity ball as written here. So we're super far from the picture here in a sense, we don't know anything. About the standard deviation depicted there. So we know that the standard deviation of T0 L dot P, well, we know it's at least C times log L. So we know it's not order 1 for the passage time fluctuations. And we also know, and that's harder, that it's at most, so here is some progress. For a random walk, the standard deviation would be order L. You just sum, the weights along a straight line, not a random walk. For a straight line, if you just sum the weights, the standard deviation is of order, square root of L. So it's supposed to be smaller in this case. And indeed, it was shown to be smaller. It's at most L over log L. So we have a square root log L improvement on the random walk. This goes to Newman and Pisa from 95, and this goes to Benjamini-Kalai-Schramm from 2002. Later in the talk, I may call Benjamini-Kalai-Schramm Bks. So we, as you see, we don't know much about the exponent for the passage time fluctuations. The situation for the transversal exponent is slightly better. We know a version of transversal fluctuations being at least 1/3. This is Licea, Newman, and Pisa from 96, and this follows Ver Eisenman and Newman Pisa earlier work. So, so we don't know that it's super diffusive, that it's more than a Brownian motion, but we do know it's not a completely straight line segment, that it fluctuates at least like L to the 1/3. It's something. All right. So this is the sad situation of the model, and there is a book that summarizes a lot of progress. 50 years of FPP, 50 years of FPP by Uffinger, Damron, and Hanson from 15, I think. It's a very nice book, very good, and I recommend you to look at it if you want to see some additional facts and pictures and the proofs. Okay, I should say, I won't write that there is another model that we do understand a bit better if you modify first passage percolation into what is called directed last passage percolation. Then there are a few exactly solved cases for which you have exact formats, in which case all of this basic picture is understood and more, much more. But it's not the same model.
Exponential distribution, right?
You need specific weight distribution. For instance, exponential. Here, I didn't allow exponential, but I could have allowed it. This is mostly for simplicity. And but even in the exponential distribution case, it's not a ball. But in the directed, and we don't know what it is. And in the directed last passage percolation, I meant not a Euclidean ball. Then we do know what it is in the exponential case. Yes, the directed last passage percolation, we have exact formulas for the norm, which is indeed strictly convex parabolic, just a simple parabola.
So how difficult is this Schramm upper bound on
the Benjamini-Kalai-Schramm upper bound is following from the theory of influence. By the way, I only noted them, but they did it for a weight distribution, which is Bernoulli, and there were extensions, Benaim was in all, and others. It follows from the result of Talleyrand, but what you need for that as an input is a bound on the influence of edges.
Yes.
So you need to know something like it is unlikely that the path passes through any specific edge. Far from the endpoints. Near the endpoints it has to pass, but in the middle somehow. And I will elaborate on a similar problem in a second. You need to know something, but it's okay to know it on average in some sense, and they managed with that.
Yeah, I have one more question.
And then it follows from a result of Talleyrand.
I see. So it's, yeah. So I have one more question, whether if you do this, you can formulate versions of this, I guess, in the continuum, right?
Well, yes, definitely. You can take R squared, and you can have some smooth continuous environment. That's right.
But you can make it smooth and
and you can make it rotation invariant if you do it in the continuum. So it's possible in the continuum to have the unit ball the Euclidean.
And then do you know much more?
And then you know a little more. No, yeah, you do know a bit more, but there are also additional complications. For instance, one easy way you can in R squared put a Poisson process and say that whenever you pass through a Poisson point, then you deduct one from your weight. But as you go along, you also pay for how far you go. So you want to catch as many Poisson points without going too far, without having too much length. That's a nice way, and it will be rotationally invariant if you do it right, and then it's a ball, and you know better fluctuation bounds.
You have, but you still don't have.
You don't have
you don't get much improvement over these.
You do get, yeah, you do. So depending on where you are, you could go as high as 3/5 for psi, and you could go.
That's pretty good.
Yeah, 3/5 is getting closer to 2/3. It's super diffusive. That's right. So already Newman and Pisa noted that under some curvature assumptions here, you could go to 3/5, and you get a better lower bound. So you get an exponent. You could go as high as L to the 1/5 for the lower bound in the standard deviation, but from above you don't get the improvement immediately. Right. So that's right. So if you add rotational invariance, you can go a bit further. That's one, but not to the full picture. So far. Okay.
Is this book by
Uffinger, Damron, Hanson.
do they talk about the continuum case or not?
No, mostly on the lattice case. That's the case that has received the most attention.
And are there exponents that are believed to be, I mean, you can do a similar thing in 3 dimensions?
Okay, that's a good question. So when you talk about 3 dimensions, you could have 2 generalizations. I will explain in a minute how another one can be formed. But I think the one you have in mind is that you have a random metric in 3D, and you have these 1-dimensional geodesics in it. Supposedly by the physicists, for every dimension, you have a psi, a transversal fluctuation exponent from a straight line, and a chi for the standard deviation. But except for a scaling relation, which I didn't write, which should hold in any dimension. So scaling relation that is supposed to be for any dimension is that chi equals 2 psi minus 1. And you can see that it holds for this choice. Then except for that, the physicists don't know what the exponents should be. And they don't even know if there is a dimension when you become, on the one hand, diffusive, and on the other hand, when the standard deviation of the passage time is order 1.
There's no known upper critical dimension.
No known upper critical dimension, and some, I believe, discussion or controversy on whether it exists in this sense. That's right. And even 3 dimensions, it's not. So maybe 3 is more convincing.
They must have numerical stuff.
That's right. Yeah. So I think there's.
But there's no 4 minus epsilon. There's no epsilon expansion or anything like that. That seems to be useful. I mean,
I don't know if an epsilon expansion, but there are, I think, conflicting opinions. So maybe there are.
Well, if there's a critical dimension, then it's hard to do an epsilon expansion.
Right, but maybe some people do. But I think some people think there is an upper critical dimension. Maybe some people think it's 8, and others think that it's I know 2, and others have some other ideas. So maybe for each of these predictions, you can have an epsilon expansion.
That look very useful.
Well, maybe one of them is right. Yeah. Okay, and there are also other perspectives. So I just wanted to give this, especially because I'm interested in some of them. So one perspective is a growing aggregate or a growing ball. So this one is the one I won't spend time on, so I'll just say it briefly. Instead of thinking about geodesics in a random metric, you can think of these lengths as indeed the time it takes you to go from one point to the other. And now think about taking water, pouring it into the system at U and letting it spread. On each pipe, you have the time it takes for the water to go. So then you're starting to pour the water here, and at time t, you see that the water is already filled up in this region. Maybe there's a little hole here that wasn't filled, and maybe there's a bit of fluctuation here. But generally, in a time slightly bigger, you see a bigger growing aggregate and so on. So with this idea in mind, then these exponents are measuring the fluctuations of the growing aggregate, and B is the global law of large numbers for it. That's a pretty similar perspective. And here is a disordered systems perspective, and more sophisticated than that in a sense. So this is the disordered Ising ferromagnet. So this says the following. In the Ising model, you have configurations attached to the vertices, spins attached to the vertices of the square lattice. And in the Ising model, the energy of a particular configuration is minus the sum over all edges of sigma u times sigma v. So this, I hope many of you are familiar with. This is the Ising model. Now, in the disordered ferromagnet, I replace this by something that looks somewhat innocent. I replace by h tau of sigma, which gives a random energy to a configuration. However, similar looking, for each edge, I have its own coupling constant. But these taus, they will be the taus from here, so they're still non-negative. So it is clear that you still would like to have a plus next to a plus and a minus next to a minus. So this is an Ising model, just with random coupling coefficients. And it might look that at least at low temperature, this should be innocuous, maybe. But here is a non-trivial question. So basic question. So a ground configuration, sigma is whose energy cannot be reduced by changing finitely many spins. Finitely many spins. And an example of that is the example is sigma, which is all plus, or sigma, which is all minus. This is clear that if you have the all plus configuration, you change finitely many spins, then the difference in energy, well, for the edges touching where you changed, among the previous energy and the new energy, it doesn't become lower, so it doesn't improve. So it's clear that the constant configurations are ground configurations. Which other configurations are ground configurations? So a basic question is, are there other ground configurations? So let's try to form one. So suppose that they have a ground configuration for the disordered ferromagnet. So that means that, well, I'll just try and make the simplest possible one. Can it be that they have pluses which surround an island of minuses like that? The answer is no, because if I then change these minuses to a plus, I gain energy on the boundary. So this will not do. So it must be that the separation between pluses and minuses forms an infinite interface. Let's try and do that. Let's form an infinite interface. Can this happen? Well, the property that is required for this to happen is that if I take any 2 points along my interface, then there is no way to change the spins, finitely many spins, and improve the energy. But if you think about it for a little while, this exactly says that the path between these 2 points must be a geodesic between U and V. A geodesic in the metric that was discussed before. And we have to have it for any 2 points. So in fact, the answer to this question is yes, if and only if there exists infinite bi-geodesics, two-dimensional infinite geodesics. And then the conjecture is that they do not exist. Okay, and you were asking about generalizing to higher dimensions. You can also generalize this perspective, in which case you wouldn't get to a, if it's sigma from ZD to minus 1, 1, it wouldn't be, the separation of pluses and minuses wouldn't be a line, it would be a surface, a hypersurface. And our conjectures, and my student has a work in progress on that. Okay, so the conjecture is that they do not exist here. So let me say now, in the title of my talk, I have Coalescence of Geodesics and the Benjamini-Kalai-Schramm midpoint problem. Let me now give the Benjamini-Kalai midpoint problem from this perspective, because I think it also is a nice perspective. So Benjamini, maybe I'll just call it BKS midpoint problem.
So it's believed that the two standard ground states are the only ones in 2 dimensions, right?
That's right. Yes.
But one can't show that.
In the exactly solved models, one can show that there are no infinite bi-geodesics in the suitable sets. But in this model,
it doesn't apply here, does it?
That's right. No result in that exists.
Because Those exact ones require certain special distributions.
Because those exact ones are not this model. They're not directed, they're not first passage percolation, they are directed last passage percolation. Roughly speaking, the main restriction is that the geodesic must be a function above a base. Cannot make a backtrack. So in my pictures here, you see it's not a function above the base, but it has these overhangs. That's the directed requirement, and that simplifies a lot of things. And then after that, you need to choose specific distribution.
Yeah, I think that's also a very serious problem, right?
Yes, that's right. Okay, so what about the Bks midpoint problem? You may imagine trying to create a bigeodesic in the following way. So attempt, okay, so I'll just draw the picture. You may imagine, how about I take pluses next to a minus with so-called Dobrushin boundary conditions. So I have a domain, and I force the domain wall outside of this domain to just look like this, and then I ask it to fill the inside as best possible. So I look at the ground state with these boundary conditions, so-called Dobrushin boundary conditions. Dobrushin. And then you can examine your geodesic, and it will, well, examine your ground state, which will just follow a geodesic, and it will look like that. You may ask, why does this not give me a bigeodesic? So if I now take this length L to infinity, why is this not a bigeodesic in the limit? And the answer is that if I look at the middle point, then unfortunately it is expected that the distance of the geodesic from the midpoint grows, that this delocalizes. It should in fact grow like L to the psi. So because of that, this limiting procedure of taking the box to infinity will not yield a bigeodesic. And this is roughly the Bks midpoint problem. So they ask to show that the probability that gamma UV, the geodesic from U to V, is within or passes within distance 1 of U plus V over 2 goes to 0 as the distance of U and V goes to infinity. That's what they ask to show. So you take 2 points, U and V, you mark the midpoint, you want to know that it's highly unlikely that the geodesic exactly passes through this midpoint. Likely it will miss it. And this is the question posed in 2002. Okay, but the fact that it's from 2002 somewhat indicates that it's not an immediate question. They didn't know how to answer it. So just again to show you that we don't know so much. However, it has been answered by now. Alberg and Hoffman gave a proof. It's not simple, but it is a proof in 2016. And this was after another work that had the differentiability assumptions by Dameron and Hanson. And with huge assumptions, then there is also Alexander. So this is Dameron Hanson 15. And there is also Alexander 20 with strong assumptions. So I don't go into the work of Alexander here. So one thing though about the Bks midpoint problem is that this is non-quantitative. So they know that it goes to 0, the probability, but they don't know at what rate. And you may expect from this picture that the rate at which this goes to 0 probably should be like the distance UV to the minus psi, because the exact position that you are in the middle should be roughly uniform on your standard deviation here in the height. Okay, so we don't know that. Okay, so this was all an introduction to the model. And now let me say something of our results and something of our clips. So the results are all joined with Dembin and Elboim. Doris here. So our results. So let me start by saying that we do have a limit shape assumption, though we think it's rather mild. So I will mention something about it. Limit shape assumption, denote by sides of B the number of extreme points of B. So for instance, in the example of the L infinity ball has 4 sides. Okay. But if the shape is not a polygon, if it's this shape, then the number of sides is infinite. Okay, so this is the notion of the number of extreme points of the unit ball. So we assume that the number of sides is at least 32. You can easily convince yourself that 4 is the minimum, and then it's divisible by 8. We don't want it to be 4, 8, 12, 16, all the way up to 32. So it's not that we rule out finitely many shapes, but okay, finitely many number of sides. And unlike many of the other assumptions about B, like strict convexity or things like that, this we actually know that it holds. So we prove it holds for a class of distributions, class of edge weight distributions. I won't go into that, but roughly for perturbations of a constant. So if you know, a bit strange, if all the passage times were 1, if all of them were equal to 1, then you'd have just the L1 metric ball. And if you have a perturbation of 1, if it's 1 plus something small, plus 1 plus a small uniform, then we know our assumptions hold. So immediately you go out of the L1 ball into something with many sides. But if it's a big perturbation, we don't know. Anyway, here is our first theorem. So our theorem may be stated roughly as follows. The coalescence exponent is at least 1/8. So what do I mean by that? So we mentioned earlier this idea of highways. So if you think in terms of highways, then you may have the idea that if a geodesic starts from here and goes here, and another geodesic starts from here and goes there, then the way they will look is that this will have some appearance, but then this one, because this has probably found the highway, I mean, likely it's found the good way, so probably this one will only differ from it in the beginning and the end. That's a reasonable picture to expect. However, it was not known before us in this generality. I mean, it wasn't known except for the exactly solvable models, and maybe under a very strong assumption by Alexander. Yes, also under so assumptions of exactly solvable models in Alexander. So we're able to prove the following. So let UV be in Z squared, and let's call L the distance of UV. Then the probability that there exists, sorry, I should have written for any alpha less than 1/8. So for any alpha in the 0, 1/8. 1/8 here is the 1/8 here. So the probability that there exists 2 points
The distance is in this metric, right?
This I didn't specify. This is say L1 distance.
Okay.
Say L1. E.g. L1. Not in this metric. In the metric, it would be random. I just want to take a non-random distance, the first order. Probability that there exists 2 points which are close to the starting and ending point. Z is close to U by less than L to the alpha, and W is close to V by less than L to the alpha, such that gamma UV symmetric difference gamma ZW. So I look at the difference of the two geodesics, and let's say I just put something, we can do more, say greater than L over log L. So let me try to explain what is written here. So this is a symmetric difference. So I'm looking at the geodesic from U to V. For instance, maybe this is U, and this is V, and this is Z, and this is W. So I have these 4 points, U, V, Z, W, and Z is close to U, and W is close to V by L to the 1/8. And I'm saying that the two geodesics, they don't differ by much. The chance that they're going to differ to the minimum distance that the number of edges they have is L. The chance that more than L over log L of these edges are distinct, that they haven't coalesced, these parts at the end, the chance of that is very small. It's smaller than constant L to the minus some other constant that depends on your choice of alpha. So this is one way to state our result. And we have other additional formulations. So we're actually saying a bit more that if you have U here and V here, then simultaneously every starting point in a box around VU and every starting point in a box around V will have a coalescing geodesic. Whatever starting and ending points they pick here and here, the geodesics will coalesce. Okay. This is this idea that the probability that there exists inside. Okay, so this is our main result under the limit shape assumption here, and that we actually know holds for class of distributions. And let me mention a corollary for the Bks problem. The result implies, under the same assumption, a positive solution to the Bks midpoint problem. So corollary, Bks midpoint. So if I take UV in Z squared, and again, L is the distance of U and V, then the probability that gamma UV, as we had there, passes. Let me just ignore this rounding issue and say passes at U plus V over 2, within distance 1, is again at most power. So this is a quantitative solution of the Bks midpoint problem, earlier solved by Elboim, but non-quantitatively. So this is the first quantitative solution, except again in these exactly solved models or with assumptions of the exactly solved models by Alexander. Okay, and maybe I'll just say a few words of the deduction. The deduction theorem to
what is what do you have there?
Okay, yeah, I didn't write all of this, but this should be preceded by there exists CNC positive. Okay. So these are universal constants.
But you don't.
Also in this theorem, there is some universal constants. CNC of alpha. We do quantify it. So you could have we have a 1 over 17 or something. It's a specific one. I mean, you have to quantify there and there, it is quantified.
But you expect it to be,
1 over 2/3, but in a sense, the prerequisite for knowing that this probability decays like 2/3 is to know that the transversal fluctuations are at least 2/3. And the only thing we know is that it's at least 1/3. So you may expect that the best we can do is 1/3. And indeed, our proof method kind of builds upon this fact that is known. We have our own proof of it, but it's a similar methodology in some sense. And then you may expect us to get the coalescence exponent of 1/3. We don't manage to get there, but we get the 1/8. So we lose a little. Yeah, at least it's positive. There was no exponent before. So let me say something about how the Bks midpoint problem follows. That's fairly easy. Suppose that, so let's denote by P the probability that's in the this problem. And let's imagine that this event happened. So if this probability is high, then this event could happen. So we have we have U, we have V, and we have the midpoint over here, and the event actually happened. This passed through the midpoint. Okay, then because of coalescence, if I take any geodesic that is displaced from U, so let's take a displacement X. So I take a displacement X and I move to U plus X over here. And I move also to V plus X over here. Then by coalescence, which happens with good probability, then this path and this path will also pass through the same point. So we have a whole box of geodesics that passes through this point. But by translation invariance, if you think for a minute, the chance that U plus X to V plus X passes through this point is the same as the probability that U and V pass through the points, the displaced point in the middle. So if I move, I'm going to move the center to a center minus X. So U plus V over 2 minus X. The chance that that the green geodesic passes through this point is the same as the chance that the original geodesic passes through the displaced point. But this one passes through, I mean, all of the guys in this box pass. So eventually the idea is that the expected number of points that the blue geodesic passes in the green box is proportional to its volume. So the expected intersection of gamma UV with green box is at least P minus a little, let's say half P, times the volume of the green box. And all this if P is greater than the coalescence probability. P is greater than, say, twice coalescence probability.
So is this the same as just saying that?
This is translation invariance.
But is it the same as saying that if I take a Debruchin boundary conditions in a very large box, then I'm going to have L to the 1, L to the minus C, no, L to the C fluctuation of the interface around the origin.
Yes, that's right. L to the C with C, which is 1/8 eventually. Well, the probability there. Yes, that's right.
Yeah, so that you know you have something.
I think it's 1/16 maybe. Yeah, that's right. So the middle. So this version of psi
special, you could probably work.
Yeah, you can do it in any position.
Yeah.
But I'm just saying that this version of psi was not about any specific location, but rather somehow an average or L infinity, and this is catching specific points.
Oh, okay.
That's the difference.
Okay.
So it's much harder to catch the specific points.
Yeah.
Okay, and anyway, this is a contradiction. This is a contradiction that you visit so many points in the green box. So you can easily convince yourself that the geodesic that enters the box somewhere must leave the box after a linear number of steps in the side lengths and not a volume number of steps, because otherwise it spends too long in the box. It could have made a shortcut. So contradiction if P is large. So you can get this very easily. Okay, I don't really have almost any time left, but in what I do have, I'd like to tell you something about the proof of the coalescent result. It will be pretty brief, but I want to tell you something about it. I'll just do it with pictures. So we have U and V. And we want to know that if we take a Z and a W around U and V, so in these green boxes, then the geodesics will coalesce with the geodesic of U and V. So the first thing we do, we say, okay, let's take a point far above U and a point far below U, and one here and one there. So this is far above is roughly L to the 1A, maybe a little bit less, like so. And then we look at the geodesics of them. So we have this orange geodesic and this orange geodesic. And we call this gamma plus and gamma minus. So if we can show that the picture looks like this, that gamma plus intersects gamma minus, then we know that anybody in the middle, it's going to be trapped here. We call this a trap, because anybody in the middle will need to somehow pass here, and it will be difficult for it. The only way it can avoid being in the trap and coalescing is if it goes around. In principle, it could go around, but this is where our limit shape assumptions enter, that it doesn't go around. So limit shape assumptions. So I've told you that if we had a L infinity ball, then it wouldn't be strange for the geodesic to deviate up by L. You can imagine that more and more sides somehow constrain it. What they actually do is to say that it doesn't wander far in the completely wrong direction. So we need to know that the geodesic of a point doesn't say go up by more than L to the 1/8. And the limit shape assumptions can do that. Show ordering is preserved. So the first step is to create a trap. After we have the trap, we only need to talk about gamma plus and gamma minus. So need intersection of gamma plus and gamma minus. Okay, that's the first step. What do we do then? So now, we have to have some coalescence property, and this is our attractive geodesic idea. Attractive geodesics. We have a theorem, a proposition that says that if two geodesics spend most of their time nearby, then they coalesce, then they intersect, let's say. So what do I mean by that? In order to show that gamma plus intersects gamma minus, I will first show that this top geodesic doesn't go far from the bottom geodesic. They stay not too far away from each other. And then using this, because they mostly stand not far from each other, then they must intersect, which is what I need. How do I know that they spend most of their time nearby? How do I know that this is a likely thing? For that, we use the ordering and Markov inequality. So I'll just say it in one word. If the distance of these two is r, then the expected distance above any point in the middle, if I fix some time in the middle, and I ask when they intersect this line, then the expected difference of where they intersect this line is r as well, by translation variance and the fact that they can't, well, by translation variance, and because they can't go around each other, the distance is positive. So I can use Markov inequality to say that it isn't likely that they deviate much more than r. So if they start at distance r, then the expected difference at any position is r. So it isn't so likely that they do, say, r squared the distance, say. And then that's sufficiently good for me to say that they're nearby most of the time. Just the Markov inequality. Okay, I think I'm more or less out of time. So I don't think I'll write, but the main thing to prove is this attractive geodesic proposition. And I'll draw one additional picture and stop there, that we have this lower geodesic, gamma minus. We're going to divide it into patches. We're going to take its time axis, divide it into intervals of equal lengths. And we're going to say that the weight environment above a patch, the weight environment here, conditioned on this path, the weight environment here is stochastically less than the initial weight environment because the geodesic didn't choose to go there. So it must be that stochastically more, it must have more weight here. That's why the geodesic didn't go. That's an FKG type inequality. Conditioned on the lower geodesic, the weight here is higher than usual. And then we need to say that higher than usual means it has some chance that every path in here takes a relatively long time. And we also need to say that the geodesic, the bottom geodesic itself, took a relatively short time. And this would tell us that in this intermediate place, the geodesic, the green line could have shortcuts through the orange line, and that would have been better for it. We have this at many places. One of them will actually happen. So this very, very briefly. Okay, so thank you very much.
Questions? The arguments sound very much two-dimensional. You need to bypass.
That's right. That's right. So this is in planar first passage percolation. And we're not even completely sure whether in a higher dimensional scenario of one-dimensional pads in 3D or 4D, that the pads would in fact coalesce. They fluctuate. We do know that they have this lower bound of, well, and a different lower bound. We know that they fluctuate, but maybe they fluctuate in ways that without coalescing, we don't know. It's strange.
And you can't, numerical studies are not.
Yeah, I don't know what the numerics suggest for coalescence in 3 dimensions. I don't know if there is a numerically suggested coalescence exponent. It's a question. Our proof, in any case, does not show coalescence in 3 dimensions or any higher than 2.
Yeah,
It could, in principle, try to attack coalescence of surfaces, but that seems also quite difficult.
The only place in your proof where the limit shape assumptions appear is in this left board.
Here,
yeah,
to the trap. That's right. We also have something in the middle, but that's a much weaker assumption that we can get rid of. So it's really here about the trap. So actually, we don't need the limit shape assumption if you tell me that they stay ordered. If you do it in a slab that they can't escape, or if you have a directed model, then we don't need the limit shape assumption. That's right. Yeah, and I should have said that this type of this proposition that is only written in words here, we do know how to prove in higher dimensions. It's not a planar proposition here. So the only planar place is the fact that they want to stay close. If you know that they're close, then we know they coalesce. But to show that they stay close, we need the ordering. The ordering squeezes them together. if you have many starting positions and you want all of them to be disjoint, then they have to be close to each other. But in 3D, they don't.
Tom already brought up, a continuum model of this type. Do you have like similar statements for that? So obviously they can't exactly overlap, but
we haven't tried to prove anything. I think our proof technique is fairly robust in the sense that if you have a continuum model with which is independent and short scales, then you would be able to prove. Although there is something to be a bit careful about. Here, once you're off the geodesic, then immediately the weight environment is new. And in a continuum model, there's usually some continuity. So if the geodesic is really, really good, then the immediately adjacent points will probably also be pretty good because there's some continuity. So you'd have to have an extra ingredient where you rule out extremely close geodesics that don't coalesce. But we think it's probably possible.
can't exactly coalesce, right? Because they're unique.
The question, I think they might coalesce.
I mean, typically it's in the first order ODE, right? So if they coalesce, they have to overlap the whole thing.
No, I'm not sure that's the how it is here. Yeah, somebody mentioned to me this point, and I haven't considered it in full. I'm not sure that this is the case. It's not quite an ODE. There's a global optimization here that you're doing. You're looking for the global minimum that locally you're minimizing, and I'm not sure it's quite right.
But can you formulate some of these same issues in terms of KPZ, in terms of just stochastic?
Sure. In the scaling limit, there is a scaling limit for the directed models, the directed landscape, and their coalescence happens. But coalescence there is like coalescence on a scale little off to the xi on the lattice model. It doesn't exactly say they are equal on the lattice level.
So there are results on coalescence in the KPZ model.
Yes, that's right. And there we know the exponent, so we know its coalescence on coalescence exponent is 2/3. That's right.
Yeah.
So the problem is that we don't know that these lattice models have the same fixed point as
we don't know that. We don't know their exponents even. We don't know that chi and xi are what they should be.
But you know that in the continuum model, in the continuum limit, with the white noise, or
no, we only know if it's exactly solved. Only in those cases. So if you start from an exactly solved model, you can calculate in some sense. And otherwise, you can start with an assumption like that. You can say, I assume my model has chi and xi, what they should be, and try to go from there. Yeah. But people do that. So they assume existence of exponents in strong sense and try to see what that gives.
but I mean, I guess there is a lot of work, but maybe they don't address the long time behavior. There's a lot of work on the continuum KPZ, right, with white noise.
Well, again, when you say continuum KPZ, I'm a bit less fluent in that, but then it's
with the space-time white noise.
But I think the notion KPZ is rather wide. I think maybe you have to specialize a bit more to say the scaling limit of this particular model, or to explain more what you have. I'm not sure.
I think what they know from what I've learned from the past is that they only know, they get local information. They don't get global information. They don't get long range information.
These days they know a lot, at least about the scaling limit of this model.
Quite a bit, right? But
maybe
globally, I don't think they know much. I think it's the same problem. But anyhow, I'm not sure about that.
At least on the so-called directed landscape, the scaling limit of the directed model, I think by now they know a lot, maybe even on the long-term behavior. Okay. But I don't know it well enough.
Any other questions? Let's thank Ron again.